So welcome Lisa Piccirillo to this conference, and we're looking forward to hearing your talk about knots. And just a reminder for those who are here in the hall that very nearby in the Newton Institute Gatehouse, or the Gatehouse to the Centre for Mathematical Sciences, which we share, I think, there are two very interesting knots on display in metal on the gate itself. So, and they refer to Conway, who I think we might hear about today. I'm not quite sure. Anyway, so it's time to hear Lisa's talk. She comes from MIT and joins us from there, as far as I know, and it's her talk is knot concordance and 4-manifolds. So please, Lisa.
Thank you. Thank you so much for having me. It's really an honor to be here, and I've never seen these gates, and I was hoping this was going to provide the opportunity. Hopefully I'll be invited back. And you know, as I was preparing this talk, I was reflecting on the theme of the conference, on the unity of math, and I was reflecting that I'm not sure the organizers should have invited me. I'm afraid I'm the sort of mathematician who really only likes one type of math. So this talk might be a little narrower in scope than some of the others you're going to see this week. So I'm going to talk about the relationships between two fields, but unfortunately those fields are already kind of rather close together. It's between knot theory and the study of the thing I really love, which is 3 and 4 manifold topology. But well, okay, that's what I got. So in order to set that up, let me start out by giving you a little bit of a taste of this subfield of knot theory that we're going to find really useful to study 4 manifolds today. And that's this field called knot concordance. So to get started, let me remind you that in classical knot theory, we say that, so a knot is an S1 embedded in S3, and we say that it's trivial or unknotted if it bounds a disk. So what you should have in mind is that this green curve here is the unknotted bounds, that bow tie noodle. And in knot concordance, our knots are still the same object. They're still S1s embedded in S3. But now we're going to say they're trivial or slice. Again, if they bound a disk, all that we're changing is we're letting the disk take up a little more space. So the disk just has to sit in B4. So it's much harder to picture that, but the schematic you should have in mind is something like this. You have the 4 ball, you have the knot that you care about sitting in its boundary, and it's slice if you can find a disk like that. And since I'm talking about surfaces in 4 manifolds, you should ask me what category I'm working in. And I actually want to pay attention to 2 categories today. So we'll say a knot is smoothly sliced if this disk is smooth, and we'll say it's just topologically sliced if it's just a homeomorphism embedding this disk. But we have some requirements on that homeomorphism, which I won't make precise, but you should think it's not like too pathological. It's not space filling. It doesn't have any cone points, nothing too bad. So what we have already is these 3 notions of triviality for knots, and clearly they inform each other. Unknots are smoothly sliced, and if you forget your smooth structure, you get a nice homeomorphism. So smoothly sliced knots are topologically sliced. But the first thing I want to tell you is that none of those converses are true. These are 3 distinct notions. And I want to unpack these a little bit, starting with B, the fact that there are smoothly sliced knots that aren't the unknot, because you know you can make the definition of sliceness and sort of that's fine, but it's I think quite hard to visualize at first like how you should go about writing down a knot that bounds a disk in B4. So let me say something about that. So to start ourselves off, what we'll do is we'll start with the 3 ball and some arc in it. And this arc is going to be properly embedded. You can choose a trivial arc, but this is going to be more interesting if you think about your arc as kind of looking knotted in the 3 ball. And now what we would like to build is a disk in the 4 ball. And so what we're going to do is we're going to take this pair and thicken it up, cross it with I. So in the picture, I had to compress the dimension of B3 so that I could draw the thickening. Forgive me, but what are we looking at here? Our ambient space is B3 thickened up, otherwise known as B4. And inside it, we're looking at an interval cross I, otherwise known as a disk. So this is some interesting embedding of a disk in the 4-ball. And so its boundary is going to be some interesting slice knot. We just have to try to recognize what knot that is. And that's not so hard. We'll just look at kind of the boundary of the schematic. So on the top, if the schematic is a can of soup, on the top, we're just seeing our original 3-ball with our original arc in it. And then the part of the can where the label goes, nothing interesting is happening there, really. It's just, ambiently, it's just this S2 times I, and the knot is just running through there vertically. So just think of that as kind of thickening of this S2 here. And then on the bottom of the can of soup, we're just seeing another copy of our original 3-ball with another copy of our original arc. So on the boundary in this decomposition of S3, S2, B3 glued together, we're just seeing basically what we saw before. For some outward normal first reasons, we have an orientation reverse out here. Don't worry too much about that. So this is an example of a knot, which you'll have to take my word for it is not the unknot, but which we've just written down an explicit smooth disk for in the 4-ball. Okay, so what about the fact that there are topologically sliced knots that aren't smoothly sliced? Well, I'm afraid I sort of already lied to you. I'm not really going to unpack this at all. This is an incredibly deep result. This was originally proven following the work of Friedman and Donaldson in the early 80s. And to this day, to build a topologically sliced knot that's not smoothly sliced, we still require Friedman for the sort of constructive side of things. So I'm not going to get into this in the first 5 minutes, but I will come back to the fact that these knots exist and why that's so very important later in the talk. Let me pause here and check in about questions about the definitions. Okay, so this is actually everything I need you to know about knot concordance for today. There's a little more to the field, but this will do. So now what I want to try to get into for the rest of the talk is how you can use knot concordance to help you understand 4 manifolds. It's not shocking that there's a connection here. There's many deep and powerful connections between knot theory and low dimensional topology in general. Loosely speaking, this is because anytime you set out to build yourself a 3 or 4 manifold, there's essentially always a knot or a link like baked into the construction of your space. And so understanding those links helps you understand your space. And conversely, understanding the spaces you can build from a link helps you understand your links. So today we're just going to be honing in on what concordance helps you say about dimension 4. And to start setting that up, I want to sort of take a minute to kind of ground ourselves in the sorts of things we try to study about dimension 4. So something maybe you already know is that 4 is the most interesting dimension. I'm sure all the surgeons in the room agree with me that that's true. And geometrically, the thing that makes it so interesting is the failure of the Whitney trick, which I won't describe in detail, but let me say sort of a consequence of that, which is that in dimension 4, you can have middle dimensional homology classes in simply connected manifolds that aren't represented by embedded spheres. This is not true for higher even dimensions. And if you could always have a sphere, then you'd have hope for classification results, but you can't. And so for me, when I want to sort of get my hands on some of the weird stuff that goes on in dimension 4, where I want to start is with manifolds that have this property. So I want to start off by giving us some example manifolds to study that have some second homology and hopefully that where that homology doesn't have to be represented by spheres. And the good news is we can do actually like the easiest thing possible. So the manifolds I want to focus on for a while are something called a knot trace. And these are the 4 manifolds you get by just taking the 4 ball and attaching to it a 0-framed 2 handle along some knot. So if you don't know what that is, or you don't build 4 manifolds all the time, don't worry. Let me tell you how to think about these spaces. What you're going to do is you're going to start off with the 4 ball, and you're going to choose some knot K that you are interested in along its boundary. And then we're trying to build a manifold that has some H2, right? So if this was like algebraic topology 1, and you ask your students how to go from here to something with some H2, what they would do is they would just take a disk and they would glue it onto the boundary of this ball by identifying the boundary of the disk with that knot. And that's what we're going to do too. So that's great. We have some H2. We're just not currently a 4 manifold, but we can fix that by just thickening that disk up in 2 more dimensions, right? And maybe a lot of people here will know that there's a choice in how you're going to do that thickening. I want the 0-framed choice. If you don't know what that means, don't worry about it. Intuitively, it won't be a problem for the rest of the day. And I won't mention framings again for the rest of the talk. So these are these really simple 4 manifolds. It's the most straightforward way you can get a 4 manifold with some H2. They have boundary, that's fine. And in fact, they're already interesting enough. So it's a theorem of Fox and Milner. It's not quite stated this way originally, but they showed in 1958 that there are knots, so that this very simple 4 manifold has this sort of interesting property about dimension 4. There's no 2-sphere generating homology. And this paper, this is the paper where they made the definition of sliceness. This is, in fact, the very first paper in all of knot concordance. So this is kind of maybe the foundational result in the field, and it kind of indicates to me that part of what knot concordance was set up to do was to help us understand 4 manifolds. But the results I kind of want to build the talk around today is even more elementary than this, which is the main theorem of the first paper in knot concordance. I actually want to build the talk around essentially the first paragraph of the first paper in all of knot concordance, which makes this observation that's now called the trace embedding lemma. And what the trace embedding lemma says is that these 4 manifolds, they characterize sliceness in that a knot is sliced if and only if its trace embeds in S4. And it's this connection. So there's a lot of ways to connect and to use knot concordance to study 4 manifold topology, but this is the one I'm going to sort of focus on as being our touchstone connection today. So let me tell you that this lemma is true in either category, and it's also true if instead of S4 you'd rather work with R4. And I like to give proofs in a talk. I like to sort of actually learn some math, and the proof of this is really cute. So let me sketch one dimension here, or one direction here. So I'll do this implication forward direction, and I'll talk about it in the smooth category. So what we're assuming is that our knot is smoothly sliced. So we'll get a picture of that going. This is a slightly different schematic. Now I'm thinking about this as being S3. There's its filling off to the left. Here's our knot, and we're assuming this knot is sliced. So it bounds some disk, and this disk is smooth. So it has a normal bundle or a tubular neighborhood. Okay. And now what we're trying to show is that this manifold here embeds in S4. So to do that, I want to get an S4 kind of present in this picture. So we'll glue another 4 ball to the boundary of the one we started with to get S4. And now I'm looking for this guy embedded in here somewhere. And in fact, it's not too hard to spot. It's this, right? This is a 4 ball with a thickened up knot stuck to the boundary. Sorry, a thickened up disk stuck to the boundary along our knot K. And the other direction is not actually much more difficult, but I'll let you work it out. Any questions so far about the definitions? Okay, so this is, very cute, easy to state, easy to prove. There doesn't seem to be that much content to this lemma, but in fact, it's really a powerful observation. Let me kick us off with a sort of stunning corollary of this lemma, which is that R4 is exotic. And let me remind you that we say that a smooth 4-manifold is exotic if there exists some other smooth 4-manifold, which is homeomorphic but not diffeomorphic to it. So in other words, a manifold's exotic if it admits more than one smooth structure. And let me also remind you that the pursuit of really simple 4-manifolds that are exotic is one of the driving questions in the field, and R4 is exotic by R4 is simple by a lot of measures. So this is a very important result. And I'm going to sketch the proof of it just now. It's a really lovely little argument powered essentially by the trace-emitting lemma. Before I make the sketch, let me comment on the fact that there's no attribution here on this corollary. That's because it doesn't appear in writing. I sort of ask senior folks who to attribute it to, and they tell me something, and then I write that name here, and then eventually that person finds me and kind of yells at me and tells me to stop attributing this corollary to them. That's happened more than once. So I'm not putting a name here now, though many people tell me I could maybe get away with writing Casson. But maybe generally speaking, this seems to have been known to folks who are around Berkeley in the late 70s. So what's the argument? Well, we're going to start off by asking the concordance folks to give us a knot which is topologically but not smoothly sliced. This is like that non-implication A from the first slide. So these are subtle objects, but they exist. So start with something like that. And now the trace-embedding lemma has something to say. It says that since this knot is topologically sliced, I can embed this trace, at least with a homeomorphism, into R4. So let me get a picture of that going. There's R4, and our trace sits in there somewhere, corners to remind you that this is not a smooth embedding. So once we have this embedding, we can consider its complement. Let's call that this manifold out here Z. Some comments about Z. So I'm just going to cut out the interior of the trace. So Z has some boundary, kind of this blue thing here. But it's also non-compact, like because R4 was. And really importantly, I want to observe that Z is just a topological manifold right now. Like, knot traces have a smooth structure, like you saw how we built them. They're very simple. You can write one down, and R4 has a standard smooth structure, but this embedding was just a homeomorphism. So it doesn't respect any of that. So Z does not come to us looking smooth. However, there's a theorem of Friedman and Quinn that all non-compact 4-manifolds admit some smooth structure. So Z doesn't start off looking smooth, but you can put some smooth structure on it. So let's go ahead and do that and call it the resulting thing Z smooth. And now what I want to do is I want to use this Z as to help me build what's going to become our exotic R4. So what we're going to do is we're going to take Z and we're going to glue the trace of K back to it. So now Z is a smooth manifold. The trace is also smooth, and it's a theorem of Moïse that those smooth structures will patch together nicely. What we get here is going to be a smooth manifold. And now I have to try to convince you that this thing is homeomorphic to R4 and that it's not diffeomorphic to R4. So let me start with homeomorphism. And to do that, we're just going to read back through the construction, but just only put on your kind of homeomorphism glasses. So what did we do here? We started with R4. We stuck some trace in it, and we looked at the complement. That was our Z. Now, this is all just messing with the smooth structure. We're not worried about that. And then down here, we took this complement and we glued the trace back. So topologically, this construction was start with R4, cut out a trace, glue back a trace. That was kind of the do nothing construction. So this is just homeomorphic to R4 essentially by setup. Okay, so what about not diffeomorphic to R4? Well, I want to start off by observing that the trace of K, it embeds smoothly in X. It's one of the sort of fundamental blocks we use to build X. And so assume for a contradiction that X were diffeomorphic to R4. Then what we would have is we would have the trace on K embedding smoothly in R4. And now the trace embedding lemma would have something to say about that. It would tell me that that means that my knot K is smoothly sliced, which it isn't. That's how we started. So let me pause there for that to sort of sink in and to see if there's any questions.
I have a small question, which is like, this isn't the, there are other ways of, well, I believe there are other ways of showing that there are exotic structures on R4. There are other smooth structures on R4. Is this way like actually sneakily equivalent to those other ways, or is this like a distinct way of showing that? I don't know if that's a very clear question. Sorry.
It's a medium clear question. There's lots of other ways to build exotic R4s, and this is certainly formally distinct from some of them. There are things called small and large exotic R4s. Small exotic R4s embed in the standard one, large ones don't. These ones are large, so certainly this construction is distinct from all of the small ones.
I was going to say, how many, I've seen constructions of uncountably many exotic R4s. How many can you construct by this method?
Yeah, so that is sort of shockingly not that well understood. So if you take two topologically but not smoothly sliced knots that aren't smoothly concordant, then it seems likely you should be building different R4s here, and people are studying that now. I know Arnima Ray works on that, but I don't quite know the answer. I know they can distinguish some of them based on the knot you used, but that would only be countably many.
Yeah. Well, it's better than one. So. Cool, thank you.
More questions?
Probably better if you continue.
Okay, well, in fact, I have a question, which is, why doesn't this work for S4? The trace embedding lemma had an S4 version, and we kind of want to know whether S4 is exotic. So we should make sure we understand why this argument doesn't like just go straight through for S4, because it seems like we have all the tools in place. So you can just start trying to run this argument and write S4 everywhere you see R4, and you'll get some distance. But you'll run into trouble at this step right here. Friedman and Quinn's theorem is that non-compact 4 manifolds emit a smooth structure. And it's not true for compact 4 manifolds. So this step here breaks down. You're not able to put a smooth structure on this complement, and therefore you're not able to sort of even build your candidate exotic S4 from this argument. At least like in full generality, you can't just say like, great, my complement has a smooth structure, I'm good to go. But this is the Poincare conjecture. We should sort of try kind of hard here. So, okay, not all compact 4 manifolds emit a smooth structure, but I don't need them all to. I would just need to show that maybe the 4 manifolds that arise as the complement of a trace embedded homeomorphically into S4. I would only need those ones to emit a smooth structure. But unfortunately, that's also not true. So there's sort of topological 4 manifolds of this type that can't be smoothed. Okay, so even for this particular type of manifold, we can't just run this argument. But this is the Poincare conjecture we should try sort of hard. Like, I don't need to know that every single topological 4 manifold that arises as a complement of a trace like this has a smooth structure. I really just need one for a knot that's topologically but not smoothly sliced. But unfortunately, it seems like even that is not going to happen. So the state of things is that for all but 2 knots in the literature that are known to be topologically but not smoothly sliced, we know that any way you embed that trace into S4, you can't smooth out the complement. So this argument on the constructive side really doesn't seem to work in the compact case. We can't build the candidates. But you know, this is the Poincare conjecture. I'm not done kind of beating this argument to death. I'd really like to know if there's anything salvageable here. And I want to point out that there is something. So what we just failed to do was build our candidate. But let's suppose we had, somehow we got this thing that's homeomorphic to S4 in some other way. And let's suppose we did it so that we had a trace embedded in it for a non-smoothly sliced knot. Then this sort of second application of the trace embedding lemma, that still works great in the compact case. And this is something that's sometimes called the concordance approach on the Poincare conjecture. Let me just spell it out in isolation. So what people who champion this approach would have you do is find a knot so that its trace embeds in a homotopy sphere. Remember that Friedman tells you all of those are homeomorphic to S4, and then just do this in such a way so that that knot is not smoothly sliced. And the reason people are sort of excited about this approach is because, you know, we don't have any tools, any sort of straight up 4-manifold invariants that could potentially distinguish a homotopy sphere from the standard one. But we do maybe have an invariant here. So there's something called the S invariant, which is defined by Jake Rasmussen. It comes from Covanov homology. And the S invariant can possibly do this. It can possibly take a knot that has this top property and still obstruct it from being smoothly sliced. Okay. So what does this approach aim to do? It sort of aims to, you know, build compact or closed exotica. And I guess as stated here, it aims to do it like in the most exciting setting possible. But you could step back a second and say, like, so far in this talk, we know that R4 is exotic. We don't have any closed exotica. What's going on in the closed case? You know, not for the Poincare conjecture. And the answer is there is that we know a lot. We got the first examples of closed exotic 4-manifolds following the work of Friedman and Donaldson in the early 80s. And since then, quite a lot has been done. I'm not going to give anywhere near a full survey. Let me sort of tell you that the state of the art, the smallest closed exotic 4-manifold is CP2 blown up twice. And in between these results, a lot happened. Let me summarize it as we got really good at constructing and detecting exotic manifolds, especially if you don't mind that the algebraic topology be quite large. But something that we did not do in between these results or for a long time since is produce exotica using an approach akin to this one. So this to me was sort of a major sticking point. Like, people are excited about this outline as potentially disproving the Poincare conjecture, but actually nobody had ever used this outline to build any closed exotica, even though we know there's closed exotica. So one of the first results I want to mention is recent work with Ciprian Manolescu and Marco Marengon, where we just use this outline to do something. This is just a sample result that's easy to state, so we can show that 3 CP2 blown up a whole bunch of times is exotic. That was already known that the result itself is not meant to be exciting. The sort of calming part is that you can use an outline like this to get exotica. And once you can, you know, once you're feeling a little better about this outline ever being useful for anything, then Ciprian and I wanted to try to understand better, like, what would it mean in practice to try to power this outline? How should you build a homotopy sphere and build a homotopy sphere in such a way that it comes with an embedded trace for a knot that at the very least doesn't look like it's smoothly sliced? Like, in practice, you know, armed with, I don't know what a computer or a whole bunch of undergrads, like how would you actually try to build things like this? And so we wrote a paper which is kind of hard to pull theorem statements out of, but let me try to make a couple. The sort of the general goal was to just really systematize a construction of candidate exotic S4s, all of which come with knot traces, and all of which are really easy to build and relatively straightforward. And sort of an indication that we did build things, many of them that are quite easy, is that me and my MacBook, and by the way, I totally cannot code, were able to sort of analyze a whole bunch, like 3,000 such examples, and find some interesting stuff. So we found these 5 knots, all of which are topologically sliced, that if any of them were smoothly sliced, then that would be great. So this second result is really not meant to be tremendously exciting. I think sometimes when I talk about this, people really want to know if we expect big things of these examples, and we don't. The point was sort of just that they show that hopefully we're on to something with this construction, like right away, basically, it can start to turn up interesting stuff to study. And maybe a reason why I'm hedging a little bit about the importance of the second bullet point is that these examples have already fallen. A graduate student, Kai Nakamura, showed that they are all not smoothly sliced. He had to come up with a new slice and subtraction to do it. It's a really lovely argument. And that's sort of okay. This was sort of always the point. And so what's happening now with kind of this project is that there's some more people working on this, in particular, some topologists who actually can code. And what we're hoping to try to do now is make a large group of people who are kind of going at this systematically, trying to understand the construction, build a lot of examples, study them in order to hone in the construction. Just get like actually trying to run this approach, something that the field is trying to do in practice. Let me check in for questions here.
Yeah, I've got a question for those who are us not working in topology. Can you remind us of what's special about this join of 3 CP2s with 20 CP2 bars? Those numbers remind me of something, but I can't remember what it was.
Yeah, it's that the K3 surface blown up once has the same intersection form as this guy, and is therefore by Friedman homeomorphic to it.
To what, to K3?
K3 blown up once.
Oh, no. Okay, yes,
Or
I
so
don't remember that. Yeah, yeah, Michael would have been very interested. Yeah,
yeah, it's just special in that it kind of has this, there's these 2 natural descriptions of the manifold with that intersection form. That's all that's special.
Are there in principle cousins of the S invariant coming from other SLN homologies or Homfly homology or anything that could also be used? Or are they?
Yeah, you bet. And where I'm stating this for plain old S sort of for convenience, but in fact, like in the computational side of this project, we use all of those. Or at least we use all of the ones that somebody's written a computer program to compute. Okay. So this was kind of a story / status update on how you can try to use the trace embedding lemma or knot concordance more generally to study exotic 4-manifolds, but something I kind of try to remind myself at least once a month is that there's more to life than exotica. So for the rest of the time, I want to point out a couple of ways that knot concordance can help us do other stuff in 4-manifold topology as well. So I'm going to give you sort of 2 more kind of touchstone applications of this lemma in particular. And the first one I want to talk about is towards a problem called geometric simple connectivity. So let me make the definition. We're going to say that a 4-manifold is geometrically simply connected if it admits a handle decomposition without any one handles. So let me say what that means for people who don't build 4 manifolds all the time. When I built knot traces, you kind of saw that we could think about those manifolds as being kind of a thickened up cell complex, right? We started with a ball, which is maybe a thickening of a 0 cell, and we attached a disk and thickened it up. And it turns out that all smooth manifolds can be described in some analog of that. And so we're saying that a 4 manifold is geometrically simply connected if you can describe it as kind of a thickened up cell complex where you didn't have to use any 1 cells in your description. And there should be a first observation that goes with this definition, which is that geometrically simply connected manifolds are simply connected, no 1 cells, no pi1. And there should be a first question that comes with that observation, which is what about the converse? Is it possible that you don't have any pi1, but nevertheless you needed to use 1 handles to describe your manifolds? And that turns out to be a very difficult question. So this is on the Kirby list and it's very open, but maybe sort of better motivation for this problem might have been that if you ask this problem for closed 3 manifolds, you get the 3-dimensional Poincare conjecture. So this problem for closed 4 manifolds is wide open. I think everybody expects the answer to be no. You should be able to not have any pi1, but nevertheless kind of need a sort of complicated handle description, but we don't have any tools for detecting that. But I think this is a problem where maybe the trace embedding lemma or concordance techniques can help. And to illustrate that, I want to say something about this theorem, which is joint with Kyle Hayden from a couple years ago, which says that the trace embedding lemma can help you do this for 4 manifolds with boundary. So let me first off come out sort of screaming and say this was not the first time that somebody had answered this problem for 4 manifolds with boundary. There's 2 other results in the literature. However, using the trace embedding lemma here has some major advantages. One of them is that our proof is just much easier than everybody else's, but maybe more substantially, the other results in literature, the way the proofs work is they build a sort of candidate counterexample, and then they very carefully study the boundary 3 manifold. And we'd eventually like to be able to answer this in the closed case. And so if your entire obstruction is powered by understanding the boundary, it's really not clear to me how those techniques are going to sort of lift into the closed setting in any reasonable way. And we don't have to do that. And then there's some other advantage, which is that we achieve some extra behavior that will happen in the closed case, but let's not worry about that. Let's instead see sort of how this problem gets to be a trace embedding lemma problem. So to do that, I need to tell you sort of three facts that'll help us see how you might approach the problem and then where the trace embedding lemma comes in. So the first is sort of what we actually in practice probably are going to try to obstruct to show a manifold isn't geometrically simply connected. And okay, what's the fact? The fact is that if you have a geometrically simply connected 4 manifold, then every H2 class is represented by a 2-sphere, which is almost smooth. It just needs to have a single cone point singularity. So I said, like, when I started talking about 4 manifolds, that we're very interested in what surfaces represent their H2, and you can't always get a sphere, but if you're geometrically simply connected, you can almost get a sphere. This isn't hard to prove, but let's take it for today. And let me make a definition for these special type of spheres. We're going to call these PL spheres. You might already have a definition in your head for what a PL sphere is, and let me tell you that in this dimension and codimension, my definition is the same as yours. But again, let me not prove that just now. So when we want to show that a 4 manifold isn't geometrically simply connected, what we're actually going to try to do is find an H2 class that's not represented by a PL sphere. Okay, and what's the state on how able we are to do that? Well, we're very able to do something close. We have a lot of tools in the literature for showing that there are H2 classes not represented by smooth spheres. This is like the thing we try to study geometrically. We have tools for that. But we don't have any tools for obstructing a PL sphere representing a given homology class. I mean, if we did, we would be able to just solve the problem in the closed setting. So this is kind of the state of things when you come at this problem. And what the trace embedding lemma will turn out to be good for is allowing you to say, if you had a PL sphere, then you would have a smooth sphere, and that's something you can obstruct. So let me show you how it's gonna let us do that. So the way the proof goes is we start off by building a candidate. So we build this 4-manifold, it's simply connected, and we're gonna arrange for two things to happen. First off, we want it to have a homology class that's not represented by a smooth sphere, and that's something that we have tools to be able to do. And we also want to do it so that the whole manifold embeds in S4. And this is where I'm using the fact that, like, this is where I'm reliant on working in the case with boundary. Closed, interesting 4-manifolds don't embed in S4, but there are manifolds with boundary that do. So I don't care what the boundary is, but it does have to exist for this to be possible. Okay. So here's a schematic of that. This is our 4-manifold sitting in S4, and now we're going to assume for a contradiction that this same homology class did have a PL2 sphere representing it. So there's the schematic of that, and what I want to try to do is now take a neighborhood of this PL sphere. But this sphere, it's not smooth. It doesn't have a standard neighborhood in any reasonable sense. So what we're going to do to make sense of a neighborhood of it is I'm going to first take a ball neighborhood of the cone point. So this is just a little ball in S4 that contains the cone point. And then away from that ball, the rest of my sphere is smooth. So that has like a standard neighborhood. So take that out here. So this is this kind of neighborhood of our PL sphere. And it should look kind of familiar. What is it? It's a ball with a thickened up disc stuck to it. So that's going to be a knot trace. We have no idea what the knot is, right? Like, I just assumed this sigma existed. I don't have any control over what knot this is, but whatever, the neighborhood of the sphere is some knot trace. And we do know one thing about this knot, or this knot trace, which is that it embeds in S4, right? This whole thing kind of happened ambiently. So I don't know what the knot is, but I do know by the trace embedding lemma that it's slice. So then I can come back and look at this picture. In particular, I can look at my, well, in fact, sorry, let me back up. What does it mean for a knot to be sliced? That means it bounds a smooth disk in the 4 ball. So in particular, if I look at this little blue 4 ball here, you know, what I see is this kind of cone point disk, but I know that my knot actually bounds a smooth disk. So I can replace the singularity with the smooth disk for the knot, and suddenly I'm in business, because now I have a smooth sphere representing my homology class, and that's not supposed to happen by setup. Let me again pause there for digestion and questions.
So what would happen if you would take 2 of those smooth 4-manifolds and glue them together along the boundary? I mean, what is wrong? In literal practice, for the examples we built, you get something very boring. I think you get like S2 times S2 for the sort of baseline examples for us. Like, unfortunately, they seem to, for one, the obstruction vanishes, and for 2, in practice, they actually seem to turn out geometrically simply connected more than you might expect. But for really gnarly examples, maybe that's a good source of potential closed examples. Okay. So we have 4 minutes and one more application. Let me tell you about unfortunately an application going for me in the wrong direction. So this is going to be how to use 4-manifold topology to answer a problem in not concordance. I guess sometimes you sort of take what you can get. So maybe one of the first like practical problems in not concordance is if I give you some knot, determine whether it's smoothly sliced or not. And this is something we're very good at, especially in the obstructive direction. And the reason for that is because there's just tons and tons of sliceless invariants that have been mined from like all modern branches of topology. And none of these invariants are perfect, but because there's so many of them and they come from many disparate fields, taken together as a suite, this is a really powerful set of tools for obstructing sliceness. But there are still a few types of knots where, you know, maybe the knot's not sliced, but it's a little hard to show that. And one of them you've already seen. It's hard to show that knots which are topologically sliced aren't smoothly sliced, right? These are these subtle objects that give you exotic R4s. And so in particular, if you have a knot that's topologically sliced, none of the sliceless invariants coming from the algebraic topology of associated manifolds can show that it's not smoothly sliced. But any of these tools here can. Another type of knot that's sort of hard to show isn't smoothly sliced is, stated vaguely, knots that just look really similar diagrammatically to a knot that is smoothly sliced. The invariants just have a hard time distinguishing them at all, and therefore the invariants think they look sliced. And there's a particular notion of similarity. It's called being a positive mutant, where this is actually really subtle. So in fact, knots that are positive mutants of sliced knots, all of their sliceless invariants coming from any of these theories vanish. And the unfortunate situation is that there are knots that have both of these properties, in particular the Conway knot, which you can all go have a look at tea time, I suppose, has both properties. So all of the known sliceless invariants for this knot vanish, but for 50 years nobody had found a sliced disk for it, so it didn't seem particularly sliced either. So the final application of the trace embedding lemma that I want to mention is that you can show this knot isn't sliced. And what you want to do here is you just don't want to study this knot because it's pathologically weird. It sort of accidentally sits in the intersection of these two categories. And so you're going to use the trace embedding lemma to just like get away from studying this knot. So what you want to do is you want to start off by building yourself some other knot that has the same trace as the Conway knot. And this is technical, but it can be done in special settings. And so what does this get you? Well, the trace embedding lemma tells you that the Conway knot is sliced if and only if its trace embeds in S4. And the trace on the Conway knot's the same as this trace on J. So that's if and only if this other trace embeds in S4. And then the trace embedding lemma tells you that this knot is sliced, this trace embeds in S4 if and only if this knot is sliced. So the Conway knot and this other knot are sliced together. So that's great. You just have to show that now that J isn't sliced, and that turns out to be a much easier problem. I used Rasmussen's S invariant. And I'll leave you with maybe just one final comment. Back when I was talking about the proof that R4 is exotic and why the constructive half didn't work in the compact case, I said that there are two knots where it's possible that the complement of those traces embedded in S4 could emit a smooth structure, that's these two knots. And I'll stop there. Thanks so much.
Well, thank you very much for this very engaging talk. So, any questions from the floor, first of all? And anything from online?
Nothing currently in the chat.
Oh, we've had quite a lot of questions. You inspired questions. And now we've run out of questions. Are those two knots you mentioned near the end, someone perhaps here knows, are those the two knots that are on the gate? They have 11 crossings. I just had a look, but I didn't have time to read in detail. So there are two knots with 11 crossings, and I think that's 11, isn't it?
Yeah, one's the Conway and the other's the Kinoshita Terisaki.
Which is positive mutant, I think.
Yes, that's the name. That's right. I didn't take it in, but you're right. And is that J? No.
No, that's not J. J has, I don't know how many crossings, but upwards of 30. The Kinoshita Terasaka knot does not share a trace with the Conway knot. In fact, the Kinoshita Terasaka knot is smoothly sliced. That's why the Conway knot is so hard to detect.
I see. Well, we do hope you can come here to see this gate and even some mathematicians in Cambridge at some point.
That would be great.
Okay, so if no more questions, thank you again very much.